Okay, last time we started to talk about the equilibrium of the particle in 3D. And we did one example on that, but that one was not much in 3D. So it was like that, if it's in 3D, and you can find a component on the XYZ axis, that's cool. So you can say sigma of x0, sigma of y0, sigma of z0. But usually you cannot. Usually it's not that easy to find the component of that vector on the xyz. So if you cannot resolve it on the xyz, just keep it in the Cartesian format, and we will go from there.
I thought that you could set the graph up however you wanted so that it fit however. Like in physics, they're like, well, it's not like you actually, like there is a set graph. You can make the graph wherever it's orientated however you want it to be. So like, couldn't we, like, I feel like there's no representation where we couldn't just have the origin of the one vector be the origin of the entire XYZ graph, like have that at 0, 0.
Yeah, but in case that you only have one vector, if you have a system of forces in real world, you have a system of forces applied there. However you rotate that, some of them are going to be, some of them cannot be resolved on the XYZ axis. No matter how you rotate your reference, you will get a vector that you cannot resolve it on.
Every way I was thinking about just requires a crap ton more work, so.
Okay, now let's look at the example in page 101. So, what it says that there's a box that X, Y, E system. Like that, so they can reach Z. Go through. Almost there. C and draw two loops coming from there. On and there's a box. Where is that? Go to point A here. Yeah. It's 40 pounds. It is 40 pounds. 3, so it's going to be directions of 3. Going about 8. And then 4 on 4. No. 4. So, remember what was the procedure? Draw the free body diagram, put all the forces on that reactive and active, and then write them in a Cartesian format, and then write the equilibrium equation in the Cartesian format. So here, if I want to draw a free body diagram, what point would be the best to do that?
Probably A.
Yeah, so the point A of the problem is on, because all of my forces is gonna meet there. So you can go ahead and redraw that again. By X. Y. Z. And then there I have 40 pounds just going down. From there, if I go so I have this F called T, then we'll call it here. So you can have the F going from the A to C, and then have the F going from the A to B. So these are the forces I'm going to have.
Is there no force going from D?
From D. Oh yeah, there's a D. I can't see it. Robot, so like here. Okay, so we have another force that's going to be AD. So, there. Thank you. So I have to find out these forces. Again, look at that FAC and FAB. The 40 pounds is on the axis. The FAD is on the axis. If I could have write these two on the XYZ axis, so it was easy. So sigma of x0, sigma of y0, sigma of c0. But here, I don't know those. I cannot write them on the x, y, or z axis. These two, I cannot find their components on x, y, or z axis. So I have to go and make them Cartesian. So to do that first, let's, here, what's the coordinate for the A? 0, 0, 0. For the B. Coordinate for the B.
For B? Oh, Jesus. How are we supposed to, I thought you just said it wasn't on the XYZ thing. How are we supposed to give it coordinate?
-3, -4, 8.
On the X is -3, on the Y, -4, on the Z, 8. Right? 4, 8. Got that? Got that?
Yeah.
What about the C?
-3, 4, 8.
-3, and Y is 4, and height is 8.
Yep.
And D? We don't know.
It's 3 on the x-axis. If there's only 2.
No.
Oh, it doesn't stay.
On the X, sorry. Or the D. We don't know how much is the Y, correct?
And the y would be 0, wouldn't it? Because it's on the y-axis.
But
In the book, it's drawn slightly different. So I was looking at it on the book.
what did you miss?
I'll just look at yours.
That's the X. That's the. Where did this go? Oh. The orbit rotates. Oh, so that's gonna be here actually. He's on the X. Yep.
Yeah.
He's gonna be here. And then the D's gonna be here. Yep. That is correct. Yep. He is on the X.
So we don't know the x, but we do know that the y would be 0 and the z would be 0.
Yeah, so yeah, we don't know the X, and Y is 0 and Z is 0. So is it right?
Yeah. Those are true.
Okay. So now that I have it like that, so I want to find the forces. So the one that is on this one, the weight, W, if you call this W, what's the W
40 pounds?
in Cartesian?
Oh, no. Cosine 0.
It's already on the axis.
Just do the weight just before you. No, so we need the
0i, 0k, 40z, or 40k.
Very close. 0i, 0j is going
-40.
-40. So it's going to be 0i, 0j, -40k. Or just -40k. Right?
Yeah.
What about the FAD? FAD is also on the axis.
unknown for I, but then it would be 0 for j and 0 for k.
Yeah. So whatever is the magnitude of that FAD, whatever, like here the magnitude was 40, so put the 40. Here the magnitude of FAD, whatever it is, I plus 0j plus 0k, or simply FAD I. So these two are on the axis, so it's easy to write them. But what about the FAC and FAB?
Oh, we already graphed, put everything in the coordinates, so wouldn't it, Carlos, would just be, it's like for FAC, negative 3i, 4j, 8k? Because that's its coordinate points.
Not, you can't use that chord. You have to find, remember that? You have to find the position vector.
Yep.
And then from the position vector, find the unit vector. And then from there we can get. Let's do it for the AB. What's the position vector from AB? RAB. Position vector from RAB, so it's going to be this XB minus XAI YB minus YAJ ZB minus ZAK. So RAB would be, and A is 0, 0, 0, so could have just said that was negative 3 minus 0I, negative 4 minus 0j plus 8 minus 0k, or RAB is negative 3i negative 4j plus 8k. Right?
But that got us the exact same answer as what I said it would be.
Yeah, but no. Wait. So this is a position vector. Now, how much is the length of that? How much is this?
What? I forgot my calculator.
Damn it, dude. 9.43. There's a lot more decimal places, but
9.43.
yeah. You
No.
want all the decimals? 'Cause there's more decimals, but.
You don't need to be that accurate.
Alright.
So the unit vector is going to be that divided by its magnitude, so it's going to be negative 2i minus 4j plus 8k divided by 9.43.
So it is.
So how much is going to be?
negative 3 divided by 9.43 is negative 0.318.
Alright, yeah, the next one,
Yep.
the negative 4 divided by 9.43.
Negative 0.74.
7, negative 0.74.
Nope, that's not right. Let's see, negative 4 divided by 0.42.
2j plus 8 divided by 9.43.
Yeah, 8.48 or 0.848.
0.848.
I'll let you have the first thing.
So this is the UAB, right? Now FAB would be the magnitude of FAB, which we don't know how much it is, UAB. So FAB is negative 0.318 FAB. So this is the FAB. Or I can just put it in there if you want, just put the FAB is negative 0.318 FAB. I minus 142 FAB. J plus 0.848 FAB. Okay. Now we have to do the same thing for the FAC. They're going to be very similar because so I have to go and find the position vector. So it's C minus XA, I plus YC minus YA, J plus ZC minus DA, okay. So RAC would be negative 3 minus 0 I plus 4 minus 0 J plus 8 minus 0 J. So RAC would be negative 3I plus 4J plus 8K. And as you said, when you get comfortable, you can just write it right away. Doing that.
Yeah.
Then its magnitude should be the same as the previous one. So its magnitude RAC plus 4 plus 8. So it should be the same as the other ones, so 9.43. So UAC would be RAC divided by its magnitude. So negative 3I plus 4J plus 8K divided by 9.43. So UAC would become negative 0.318 So now I have all the forces. I have this one, I have this one, I have this one, I have this one. So I have all the four forces in the Cartesian format. I'm write the rest here. So what I have is what I'm going to have the sigma f should be 0. Therefore, what I have here is that W plus FAD plus FAC plus FAB should be 0. If I put them together. So for the W is minus 40k. So that's the first one. Plus FAD is FADI. For the FAC it's minus 0.318 FACI plus 0.42 FACJ plus 848 FACK. And for the FAB, it's 17th of this one. FAB I and 42 FAB J 848 FAB K. And that is equal to, that's equal to 0. So the next part is that I will go ahead and say I will put all the I components together, all the J components together, and all the K components together. So I will start with the I. So wherever I have I, so this is I, this is going to be I, and this is going to be I. So if I go ahead and put all the one that has the I component together, I have the FAD minus 0.318 FAC minus 0.318 FAB I plus. Then I will go ahead and put all the ones that are in J together. So I have a J here, I have a J here, I don't have an other. So it's going to be ACA. So plus 42. So it's going to be 0.42 FAC minus 0.42 FAB K put together all the one that has the K. So this one has the K. This one has the K. This one has the K. So it's gonna be minus 40 plus 0.848 FAC plus 0.848 FAB K would be 0. Agree up to here?
Yeah.
Now, everything in front of the I is sigma of x. So everything here in front of the I is sigma of x. Everything in front of the J is sigma of y. And everything in front of K is sigma. So any question up to here? So let's very quickly look at what we did up to here. We first draw all the forces on the three-body diagram. Then we try to find each of them in the Cartesian format. The one that are on axis are easy to write, just write them. The one that are not on any of the axes, you have to find the position vector, then the unit vector, and then use the unit vector to find the Cartesian. So for the AB and AC, find the position vector, unit vector, and then eventually the forces. Yep. Now, the next, I will say, okay, sigma F is 0. So simply all the forces I have, add them together. So I write them there. Then when I have them, I would rearrange them in format of put all the I together, all the J's together, all the K's together. Clear up here? Okay. Now, I clean that part. So, what was the equilibrium equation for 3D?
Steady. Fx equals 0, for y equals 0, fc equals 0.
So, for 3D, fx0, fy0, fc0, right? So that's for the 3D. So if I want for the 3D, I have them. I have to write sigma fx0 sigma fy 0, sigma fz 0. So remember, the sigma fx is whatever is in front of the eye. So if I go ahead and say, okay, whatever is in front of the eye, this is going to be the FAD minus 0.318 FAC minus 0.318 FAB. This is 0. That part in front of that is 0. The same for the sigma fy. So 0.42 FAC minus 0.42 FAB is 0. And the same for this one. So it's going to be minus 40 plus 0.0848 FAC plus 0.848 FAB is 0. Background here. Now I want to solve, so this is three unknown. So I have to rewrite them in a format that I can solve it. So I will go ahead and say, so I have, what I'm going to do is that I want to have the FAD, FAC, FABs, okay? So I'm going to have FAD, FAD, FAD. I want to have the FAC, FAC, FAC. I want to have FAB. I want to write it in this form. So for the first one, FAB, what's it's just one FAB. FAC minus 0.318, FAB minus 0.318. But let me go to the color so you can see it. So it's going to be 1 minus 0.318 minus 0.318. And the other side is 0. The second one, how much is the coefficient for the FAD in the second equation?
0.
So it's going to be 0 FAD. For the AC is going to be 0.42 and negative 0.42, and the other side is 0. For the third one, again, the coefficient for the FAD,
Coefficient.
yeah,
0.
0 FAD, because I don't have FAD here. So it's gonna 0 FAD plus 0.848 FAC plus 0.848 FAB. So where that negative 40 goes, where should I put that negative 40?
Move it to the other side.
So yeah, because it's a constant, I will move it to the other side, which will be 40. So I keep it in this way: FAD, 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 FAC, 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 FAD, FAD, FAB, and put all the constant to the other side. now, okay, we have this format that we have it before, so you either can put it like that, or if I write it in the matrix format, it's gonna be 1, 0, 0, so the coefficient negative 0.318, 0.4. 18.42, 0.848, negative 18, 0.848. The unknown, FAD, FAC, FAB, and is equal to 0.040. So plug it in your calculator and it tells me FAD, FAB, those three numbers.
What was this solving for this? Similar equation solver, huh? Or polymer finder. Oh, X is 15.
So FAD is 15.
Yep. And then you might want to plug your calculators into that fraction thing again. Y is, so as you go to 1,250 over 53. So he's typing it in real quick.
23.6.
23.6, FAB, probably the same.
Yep.
Same.
Yeah.
Tons. So, any question about the part of that? Remember that when you arrange it in this 3D in 3 equation, you have to keep the FAD always zero. You have to keep it so you can enter it in your calculator. So, the next chapter, chapter 4, I'm gonna probably spend a lot of time chapter 4. It's about the moment. So, if there's a ground and there's a box sitting there, and I put the force F on that box, what would happen?
It depends on how much friction is there, but the box should move that way.
The box would slide.
Yeah, box.
Do I agree?
Assuming we're on Earth and everything is normal, yeah.
So, now if I have the same box and put the force here on the top, what would happen there?
It depends on the box. There's a lot more variables. It's either gonna tilt and be shoved, which at one point might tip it over, or it'll just slide again. It depends on the weight dispersion, disposal, just words. Center of gravity, yeah, that one works too.
So, it's either gonna slide or tip over.
You might do both.
Or I do both. Now if I make my box a little bit wrong, then what would happen?
Roll.
The rolling, the sliding.
Well, is this a frictionless plane or is this?
So there's no friction.
Well, then it would slide because there's no static friction to keep it. Yeah, slide.
So, this case, or if you have a friction there part of that is just moving, but part of that is tipping or rotating. Why it does not rotate here, but it does rotate here? It's the same box, same force.
Where you apply the force.
So why? If I come here and say, hey, instead of putting it up there, I'm putting it down here.
Like he mentioned, the center of gravity.
For sure it's not gonna,
I mean, are they all frictionless?
or assume there's friction, assume it's a normal condition.
Well, normal conditions have friction.
Assume it's normal condition, assume you have friction. So, it might slide, it might rotate. Why it rotate?
So,
Instead of sliding.
because there's a little dot in the center of that box that is, a lot of people call it the center of gravity.
Okay.
And so if you push above that dot, it wants to move over that dot.
Okay.
And so it's going to try and rotate the box around that dot so it can go over the dot.
So if it's a massless condition, assume ideal massless condition, doesn't tip over?
No.
Seesaw.
Yeah.
If I put the force here, what happened?
Jack squat.
What happened?
I said jack squat. Nothing will happen.
Okay? Now, if I put the force here, what happens?
One second.
Hit it.
So what? What's the difference between these two? The same thing, same force.
The moment.
Or let's look at the, assume there's a bolt, there's a wrench. What kind of bolt it is?
To me, this seems a lot like torque at this point. Torque. Isn't torque torque? Torque. Yes,
So if I have
that sounds right.
same thing, if I put the force here, what would happen? Assume I put the wrench here, I put the force on head of the wrench.
If you have enough force, you'll shear the bolt. But otherwise,
But you don't open it. You might cut it.
yeah. Nothing.
Yeah.
Now if I bring that force here, what happens?
Turn the bolt.
Yeah, because now it's torque.
It doesn't turn it. So and then this is the entire chapter that we're going to talk about is the ball. Exactly this. So the force can move the object or can rotate it or spin it. If it is moving it, it's a simple force. If it causes that rotate, it's the moment. It's the moment that force created that caused that object move. So in general, why do we have the wrench? Why we don't just try to use our hand and open it? And you see that if it's hard to open it, usually you get a longer, bigger wrench to open it.
Leverage. I can't remember what the property for is.
Because exactly, you want to increase the moment. The force is not going to be changed. The force that you have it, no matter what the force, put it here, or you have a larger one here, it's the same force. The only things change is the moment, and that's the moment that caused that bolt open or fasten. So in this entire chapter, we want to look at the moment and its effect, how to calculate the moment, what's its effect, how it caused the object to rotate, and in other words, in the statics view, how make sure that if you have an object, it doesn't tip over. So if you have a building, watch it, okay, the building doesn't move, also it doesn't tip over. So doesn't move is that it has to make sure whatever support we have here handle this force. But also this support here should be able to handle the moment of that force that does not let it to tip over.